Okay, this video should be a review for most of you, but it's about number systems. Essentially, the ability to convert from base 10, which is our, in the English language, it's our fundamental number system, and convert that to base 2, or hexadecimal, which is base 16. This is important in computer science because the vast majority of computers today convert all the data you see on the screen, colors, characters, numbers, everything is converted into binary because there are electrical circuits that can store binary data easily. So think of it as a whole bunch of light switches. So a 1 would be the light switch is on, and a 0 would be the light switch is off. So everything is done in binary in computers, so it's important for us to understand how to convert from base 10 to binary and some of the other number systems that are involved. Okay, so here we have base 10, and that essentially means that there are 10 symbols that you can use to write a number. This is the decimal system. Okay, if we have the number 0, that essentially represents no objects. Okay, the number 1 represents 1 object. Number 2 is 2 objects, right? All the way up to 9. Here, 6 is 6 of these objects. 9 is 9. What do we do when we get past 9? In the decimal system, we only have 10 symbols, so we start reusing them. Okay, so we place a 1 in front and then start over in the 1's place with a 0. So this 1 in front means 110, and this 0 means 0 ones. So this is 110 plus 0 ones. Okay, and that means 10 of these objects. 11 objects, we have 110 and 1 1. 12, 110 and 2 ones. Okay, so 59, I didn't draw the objects here, but that's 5 10s and 9 ones. A larger number, 2047, that's 2 thousands, that's 0 hundreds, plus 4 10s, plus 7 ones. Okay, so this gets into place values. So we have 4 digits in this number, 2047. Each X is a digit. This is the thousands place, the hundreds place, tens place, and the ones place. Now, if you recall from some of your previous math courses, the ones place is 10 to the 0 power. Anything to the 0 power is 1. So 10 to the 0 power is 1. So whatever we have in here, in this case it's a 7, it's 7 times the ones place value, which is 10 to the 0, which is 1. So 7 times 10 to the 0 is 7. The tens place is 10 to the first. The hundreds place is 10 to the second. So 10 to the second is 10 times 10. Okay, this star star means power. So 10 star star 2, that means 10 to the second power. So 10 to the second is 10 times 10. 10 to the third is 10 times 10 times 10. Okay, so this should all be review. 10 to the fourth, 10 times 10 times 10 times 10. Alright, so 10 to the fourth, or 10 to the third here is our thousands place. Okay, so it's important to recognize that these are just symbols. We have 10 symbols in the decimal system, and we use the symbols 0, 1, 2 are numerals, right? But they're just symbols representing something else. So we can use different symbols. So we think about base 10, and let's just choose alphabetical symbols, the first 10 letters of the alphabet. You can still have a decimal system using these symbols. Okay, so here 0 would be represented by A, 1 would be B, 2 C, 2 Okay, so we still have 10 symbols, they're just different symbols than what we're used to thinking about. Alright, and this is important because some of the number systems, like base 16, go past the 10 symbols we use for decimal. And you can use any symbol. You could use smiley faces or triangles or whatever. The point is it's a symbol that represents an idea. That idea is an amount of objects. Okay, and rather than writing out each object, if we had 1,000 things, we can't very well, in a document, writing something to somebody else or keeping track of things, we can't very well spend all our time writing out little stars to represent the numbers. So we had to have a system that makes it more concise. Okay, so in base 10, if we have A through J, then 10 becomes B is our representation of 1, and A is our representation of 0. So BA is the same as 10 if we use these symbols. And then you have BB, BC, and so 59, F is 5, F, and then the 9 is J. 2047. The 2 is a C, 0 is an A, a 4 is an E, and a 7 is an H. Okay? All of these are still base 10. Again, I'm stressing that because we just changed the symbols of our numerals. Okay, so in base 2, oops, there we go. In base 2, we only have 2 numerals, 0 and 1. This could be A and B, this could be star and smiley face, it doesn't matter. The point is 0 represents no items, and 1 represents 1 item. Okay? So in base 2, 0 items is still 0, 1 item is still 1. Now when we get to 2, we've run out of digits. We've run out of our symbols. So just like in base 10, we start over by adding a 1 in front and then adding a 1's place. So this is the number of 2's. There's 1 2 and 0 1's. Now there's 1 2 and 1 1, which is 3. Now we've run out of digits again. So this is 1 4, 0 2's, 0 1's. 1 4, 0 2's, and 1 4. That's 5. 1 4, 1 2, and 0 1's. So a 4 plus a 2 is 6. 1 4, 1 2, and 1 1 is 7. And now we've run out of digits again. So an 8 is 1 8, 0 4's, 0 2's, and 0 1's. A 9 is 1 8, 0 4's, 0 2's, and 1 1. The pattern is the exact same as the decimal system. When you run out of digits, you add a 1 in front and start numbering again. It just so happens there's only 2 symbols. Okay? So over here, 10, we'll keep counting. This is 1 8, 0 4s, 1 2, and 0 1s. So 8 plus 2 is 10. 11 is 1 8, 0 4s, 1 2, and 1 1. 12 is 1 8 and 1 4 and 0 2s and 0 1s. Okay. So what we see here, it's the same situation as the tens place. You have ones, tens, or the decimal system. You have ones, tens, hundreds, and thousands. This corresponds, this is 10 to the 0, 10 to the first, 10 to the second, 10 to the third. Same for binary, except it's 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, and 2 to the third is 8. Okay, so we can do the same thing with base 2 and replace the values 0 and 1 with A and B or any other character. Let's do X and Y. So in base 2, if X is 0 and Y is 1, and now we've run out of characters, so we start over. We have 1, 2, and 0 1s. So 7 is YYY, which is our last digit. If we look up here, 7 is 111. That's our last symbol there. The point is, it doesn't matter what the symbols are. It's important that you realize that. Alright, so you can keep numbering along here if you wanted. It would look just the same, except you'd place the zeros with X's and the ones with Y's. Okay, so Y, X, X, X. Okay, so in base 16 we have more than 10 symbols. We have 0 through 9 and then 6 more, A, B, C, D, E, and F. Base 16 is called hexadecimal. It's what in CSS a lot of times you can use the pound symbol and then enter in 6 hexadecimal characters to make a color. So background color or text. If you want to change the color of the text, use the color CSS property. Alright, so hexadecimal has 16 symbols. Alright, so in base 16, from 0 to 9, it's exactly the same. 10, since we haven't run out of symbols yet, we just use the next symbol, which is A. Oops. 11 is just the next symbol, B. C, D, E. 15 is F. Now F is our last symbol. So up to this point we've used all of our symbols, and F should stand for 15 because we started numbering at 0. Okay, so now we've run out of symbols, and so just like in decimal and just like in binary, we add a 1 and start numbering again. So this number, even though if it were decimal it looks like the decimal number 10, in hexadecimal it means 16. we have 116 and 0 ones. Okay, so our powers of 16, we have a ones place. 16 to the 0 is a 1. 16 to the first power is a 16. So that's our 16's place. 16 to the second power is 256. So that's our 256th place. And 16 to the third power is 4096. That's our 4096th place. Okay. So we can keep numbering these. Go ahead and finish up. That's 116 plus 1 1 is 17. 116 plus 2 1s is 18. 116 plus 3 1s is 19. Okay. So converting from base 10 to base 2. Let's pick a starting number. I picked this because there's a lot of different steps in it, and you can see how much more concise the decimal system is than the binary system. The binary system is going to produce a number about this long, like 11 digits. And so the decimal system is much more concise, and the hexadecimal system is even more concise. You see 4 digits of the hexadecimal system will get you up to around 65,000, whereas 4 places in the decimal system will get you around 10,000. Okay, so the starting number is 3,387. So first list out your powers of 2 and find the largest power of 2 that is less than the number you're trying to convert. Okay, so 2 to the 0 is 1, 2 to the 1 is 2. We've listed these out: 4, 8, 16, a couple typos here, 32, 64, 128, 256, 512, 1024, and 2048. Okay. Once we go to 4096, that number is bigger than the number we're trying to convert. So we go back down. 2048 is where we're starting. So you place a 1 in the highest place value position of the binary number you're creating, then subtract the decimal value of that power of 2, which is 2048, from the original number. Okay, so we have basically one 2048th place. Okay, and we've represented that by typing in this 1 in the position of our binary number. So now we have to make a binary number out of whatever's left. Okay, so we've taken care of 2048, so we subtract that from our number. Now we have to represent this number in binary, 1339. Okay, so you start with this difference and you basically do the same thing over and over. You find the next power of 2 that is smaller than this number, and in that position you add a 1 and then subtract. Okay, so we'll just iterate through the powers of 2. So 2 to the 10th power is 1024. 1024 is less than or equal to our number. Okay, so that means we put a 1 in our binary number and subtract, and this is what we're left with. Okay, we go to the next power of 10, which is here. Alright, 512. So 512 is not less than or equal to 315, so we just put a 0 and go to the next step. We still have 315 as the number we're trying to represent. Go to the next power of 2. It's 256. 256 is less than or equal to 315. So we add a 1 to our binary number, which means we've represented that amount, and so we subtract it from what's left, and we're left with 59. Now this is all we need to represent. So we go to the next power of 2, 128, and 128 is not less than or equal to 59, so we add a 0. Go to the next power, 64. 64 is not less than or equal to 59, so we add another 0. Next power of 2, it's 32. It is less than or equal to 59, so we add a 1. This 32 is represented on this digit. This is the 32's place. That's why we're subtracting it. So we take 59 minus that 32, and now all we have to represent is 27. 16 is less than or equal to 27. So we add a 1. That 1 represents the 16, so we've taken care of it. So we subtract it from 27. We're left with 11 that we need to represent. Next power of 2 is 8. 8 is less than or equal than 11. Add a 1. Subtract, and you've got 3 left. Next power of 2 is 4. 4 is not less than or equal than 3. Add a 0. Next power of 2. 2 is less than or equal than 3. Add a 1 and subtract. 1 is less than or equal than 1. 1 minus 1 is 0. And you add your 1. So it's kind of a long process for large numbers, but this is essentially how the number systems work. So the binary number here, which is this number, is equivalent to the decimal number 3,387. So you can go the other way. Starting in base 2, start with the same number, and start from the right side of the number and convert each place value in binary to its decimal value, and then add them all together. So again, this goes up to our places. That's hexadecimal. Here's binary. There's a 1's place, a 2's place, a 4's place, 8's, 16, 32. So if I have a 1 in the 8's place, that means I have 1 8. I'm going to add that to the total. In base 10, it's the same thing. If I have a 1 in the thousands place, that means I have 1,000 things. If I have a 7 in the hundreds place, that means I have 1,000 things plus 700 things. So 1,000 plus 700. And then, so if, let's say the number is 2,047. 2,000s, 2 times 10 to the third, 0 times 10 to the second, plus 4 times 10 to the first, plus 7 times 10 to the 0. It's the exact same thing in binary. So this is the 1's place. This is the 2's place. So this would be 1 plus 2. There's no 4's. There's an 8. There's a 16. There's a 32. And you basically just go through and add all these up. Okay, so starting on the first position, we have a 1 here, this digit. So it's 1 times 2 to the 0 power. It's 2 to the 0 power because this is the 1's place. Our total is 1. And then go move to the next digit. This is the 2's place. So we have a 1 in that position, and it's 1 times 2 to the first because it's 2 to the 0 on that position, 2 to the first on this position, 2 to the second, third, fourth, fifth. Okay? So each time we go through here, each time we switch positions, we're incrementing the power. 2 to the third, Okay, so we've got a total of 1 here. We move to the 2's place. 1 times 2 to the first is 2. Add it up to our previous total. 2 plus 1 is 3. We have 0 4's, so our total is still 3. We have 1 8, so we add that to 3, and we have 11. We have 1 16, so we add that to 11. You got 27. We have 1 32, so we add that to 27, and you get 59. We have 0 64s, so we're still at 59. We have 0 128s, so we're still at 59. We have 1 256, so we add 59 and 256, we got 315. We have 0 512s, so we're still at 315. And we have 1 1024, so we add 315 to 1024, we get 1339. And then we have 1 2048, so we add 2048 to this, and we get 3387. So the decimal number 3387 is equivalent to this binary number, 110100111011. If you go up here, that's the same, 3387 110100111011. Alright, so that's a big example for you. Most of the time the problems won't be this large, but it's important to be able to do the big ones. So I did step by step. So binary to hex and hex to binary is way easier. It's convenient because hexadecimal system is base 16, which is a power of 2. Because it's a power of 2, it makes the conversion incredibly easy. So the first thing you do when you're converting binary to hex or hex to binary is you list out the 16 binary representations of the 16 hexadecimal symbols. Okay, so 0, this is the base 10 value, it's 0 to 15. The binary value of 0 is 4 zeros. Okay, you know, we can have, even in the decimal system, we can have a leading 0. If I gave you the number 001 010, that's just the number 10. You get rid of leading zeros. Okay, I mean, theoretically you could have an infinite number of zeros in front and it'd still just be 10. Okay, so that's what's happening here. I just padded it with zeros. So the number 0 in binary is 0. 1 in binary is 0001. This is 2 in binary. You add 1. This is 3. You add 1, you're out of digits. The 1 goes here. Go to 0 there. It's 4. Add 1. 5. Add 1. So these are all of the first 16 hexadecimal values. So you notice we're out of digits here perfectly from base 2. If we added one more, we would have to pad a 1. We would have 1 0 0 0 0. Okay, but on base 16 it's the same way. If we added one more, we'd have to do 1 0, and that's 16. So what's nice about this, what this means is any hexadecimal character can be replaced by these 4 binary digits. So you can very easily translate from base 2 to base 10. So let's work through an example. We have FC39. and base 16. So F, if we look up on our chart, 1111. C is 1100. 3 is 0011. And 9 is 1001. So the number FC39, we can just swap in these binary values for each hexadecimal character. That's a 15. F is 15. Swap it in. Okay, swap that value in for C. Swap that value in for 3. This is binary 3, and this is a binary 9. Okay, so it's much easier to convert hex to binary and binary to hex. So going the other way, let's start with this binary number 1001011111. Okay, it's kind of hard to keep track of that way, so what we do is we block it off into sections of 4. So you've got 4 digits in each group. Now here we just pad zeros because you can do that and it's still the same number. Okay. So that's what I'm doing down here. Break up into groups of 4 digits and pad left with zeros if necessary. So here's the 4 groups, and you add 2 zeros to make sure we have groups of 4. Then we just look up the quads on our table that we made. And so this is a 2 in hexadecimal, this is a 5 in hexadecimal, and this is an F in hexadecimal. So this number is equivalent to 25F in hexadecimal. And notice how different the sizes of these numbers are in terms of the number of digits. So the computer basically has electronic components that can store a 1 or a 0. It basically stores an electrical charge. If it is storing that electrical charge, it's a 1, and if there is no electrical charge stored in the component, it's a 0. And so you have, tremendous number of these components representing all of the data on your computer. Okay, so this is a basic recap of number systems, base 10, binary, and hexadecimal. There's octal also, which is same as any of the others, except there's only 8 numbers, right? So that should be a good recap for you on the number systems.